Hello, welcome back. Okay, we are continuing with integration revision for year 13s. Tonight I'm gonna start from where we left it last time. I think we done 56 last time. So I'm gonna go from 57 to 69, I hope, in about 30 to 35 minutes. I've got the integrals up there, so let's not waste time. Just a piece of warning, I've got a new mic here, which makes funny noises. So if you hear any funny noise throughout the video, it's not me, I promise you, yeah, because some of them are a little bit embarrassing, okay? So hopefully there won't be any tonight. So let's get going. Number 57 is the first integral that we have to look for. Number 57 is trigonometric. It's very similar, I think, if I remember number 56, which is 1 plus the cos of x all squared, the whole thing over sine squared. I just want to check if that's a plus. It is a plus. So how do we do an integral like that? Well, quite obviously we're going to expand the bracket and split the fraction. So I'm going to do that very, very quickly. So 1 plus 2 cos x plus the cos squared of x over sine squared of x dx. And I'm going to split the fraction, not showing an in-between step. 1 divided by sine squared, I'm going to write it as a cosec squared of x. And the reason I want it as a cosec, I'm going to write a little fact here, which we've seen before. The differential of a cot is actually minus cosec squared of x. So it's in your formula booklet, so you ought to know it or look it up under differentiation. Then I have to divide 2 cos x by sine squared x. For this particular one, it's a little bit tricky one. I'm going to put some extra workings to remind ourselves, because it takes a little while for that particular one to sink in. And lastly, we got cos squared x over sine squared x. And cos squared x over sine squared x is a cot squared x dx. And let's evaluate our position just to see what's going on. This is straight away we can do. Cot squared. How do we do cot squared? It's actually doable via trigonometric identities, which I'm going to do in a second. But this particular one, the one in the middle, is the one that normally causes problems. So I'm going to rewrite it and remind you at the same time how this is done in the most standard way. Cos x over sine x. What happened to sine squared? I'm going to write it as 1 over sine squared x. And y, oops, not sine squared, sine x. It's very late in the day, so probably tonight I'll be making loads of mistakes. I do apologize. So that's just check, it's exactly the same thing. And now I'm gonna do a few transformations here to actually get my integral ready to be done. So the cosec squared I know is doable, so I'm just writing it again. Now this is plus 2 cot of x times a cosec x, and the cot squared, it needs to be switched into cosec squares. Identity 1 plus cot squared x is equal to cosec squared x. So I'm going to write this as a rearrangement, cosec squared x minus 1. So this is your cot squared standard trigonometric identity dx. Okay, so this simplifies now. And the question is why we've done that, which I will explain. I'm going to write the result down. We've done it a few times already in this particular revision. I got 2 lots of cosec squared x rather. These are the 2 bits there. I'm going to put the minus 1 next, and then I'm just going to rewrite the 2 cot x cosec x dx. Well, this is a standard differential. You ought to know that the differential of cosec is in the formula booklet as well. And differentiation differentiates to minus cosec x, oops, I keep putting squares tonight, I don't know why, minus cosec x cot x. There's no square there, I do beg your pardon. Okay, so this is exactly the same but for the minus sign. So we're ready to integrate. That comes from a differentiation of cot. It's the first line that I've written up there. It produces a minus cosec squared, so we need the minus to take care of that. And of course, there should be a 2 there. This is a minus x, done. And this, we need to differentiate. A cosec produces the negative of that, so we need the minus. And of course, let's write the cosec down first of all. And of course, we still got 2 to take care of, plus c. And that's the answer to this particular one. This is not very pleasant. I just hope you don't get trigonometric integrals on your exam, because there can be a mess. And if you freeze under exam conditions and you mix your identities, then this normally they can go horribly wrong. So you want more standard stuff. What you want in your exam really is partial fractions, which are very easy, integration by parts, and in fact and substitutions. Nice substitution, not too bad either. So the next integral now is 1, sorry, I'm copying the different line. It should be x. What am I writing up there? I don't know. I don't have a fraction. I do apologize. Double checking. Very tired tonight I am. X sine 3x. I had already 4 lessons today, so I'm brain dead. All right. How do we integrate that? It's as standard as it gets. Is integration by parts. Product to different mathematical families. Algebraic versus trigonometric. Okay. I've done again a lecture integration by parts of how I do it. You can use your formula, you can use your own setup. I'll put the x on the top left, that's the algebraic bit, and I'm going to put the sine of 3x on the bottom right. I'm going to differentiate the x into a 1, and I'm going to integrate the sine 3x back in here. I need the cos of 3x, cos differentiates to a minus, the minus take care of it. It also produces a third. So this is now my setup. And the answer is always equal to, when I have integration by parts, the product of this particular column. So that is minus a third x cos of 3x that I've got in there, minus the integral of this particular diagonal, the product of this particular diagonal. So it's minus a third cos of 3x dx. I'm gonna kill these minuses because they're very messy, and you should do as well. No need really to copy it again. I did record it and then I safely made it into plus. Copying the first thing again, x cos of 3x. And to integrate that, we're starting by differentiating a sine 3x. Sine differentiates to a plus it is, and you also produce a times 3. So divide by a further 3, third divided by 3 is 1/9 plus c, and 57 is, actually that's not 57, I didn't change the number from the previous one, that's number 58, is done. Number 59 is coming next. Okay, I cannot fit it in here, so it's a little bit of workings for the next one. So let's clear the board again. My board also needs a good clean, but I don't have time, so I'm gonna have to make do with this. I hope it's not too dark when you look at this, very purpley somewhere where I'm rubbing now. So hopefully you can still read my writing. So number 59 is the integral of 2x over 2x plus 1 all cubed. Okay, what technique is this particular one? Bottom differentiate to the top? No. Can I do partial fractions? The answer is yes, you can. It's going to be very lengthy and unnecessary for this. You can actually split this into something over 2x plus 1 plus something over 2x plus 1 all squared plus something over 2x plus 1 all cubed. Is it really it will work? Definitely will work. Is it the way you should do it? Probably not. I wouldn't show this method. It's not really sensible. I can do parts, which is just crazy. So the only other thing that's left which is sensible is a substitution. Okay, this is a mess. I tried to split my integrand, so I'm gonna go for a substitution. I'm gonna put the workings here. The obvious substitution is u is 2x plus 1, not the whole thing of course. So immediately I differentiate. So that's 2, and make my dx the subject, so that is dx is du over 2. Okay, so far so good. Putting my stuff in, and what happens with this one now? The 2x I leave him as he is. He's happy. These are called u there, so that's gonna be my u cubed, and my dx is du over 2. Little tidy, I always recommend it. And there's a 2x on the top and a 2u cubed at the bottom. du, we need to lose this x, okay, because everything needs to be in u. I can cancel the 2's, but I won't, and I mentioned several times why not. For this particular one, I'm gonna need to rearrange this for x. So 2x is u minus 1 is kind of good. I don't want to divide by 2. See, if I cancel these 2's, I'm going to have to get x, and x now will be a double fraction there. I don't want to do it. That's good as it is. So I'm going to leave it as is up there. This mic is getting longer and longer by the day. So what do we have in there? 2x is u minus 1, and the denominator is 2u cubed du. I'm going to split the fraction. So I'm not going to solve the extra step. U divided by 2u cubed. I'll go half, 1 divided by 2. U over u cubed is u to the minus 2. Minus, that's the 1 there. And I've got a half again, 1 divided by 2. And this, there's no u on the top, so I'm going to write to the top as u to the minus 3 du. And now this is just a straightforward integration, just indices. U to the minus 1 with a minus a half in front of it to make it work. Increase the power again, u to the minus 2. We divide minus a half by negative 2, so that's going to be now a positive quarter plus c. And of course, we must not forget to go back into x's. I'm going to write this bit first because it's positive. A quarter, u is 2x plus 1. Look on the side there, to the minus 2. You can write at the bottom, but it's probably better to leave it like this because I got this quarter, it looks very ugly. Minus a half, 2x plus 1 to the power of minus 1 plus c. Question done. This particular one, for those who they saw a lecture of mine, I think the lecture was called Integration by Substitution without the substitution. This actually can be split in a very clever way. If you look at the 2x practically there, really, I'm not going to show full workings for that. I'm not even going to integrate, just to show you what I'm going to do there very, very quickly, and you can take it yourself from that line. I'm going to put 2x plus 1 minus 1 on the numerator, and then 2x plus 1 as it was at the bottom. Now I'm going to split the fraction. That divided by that should give me 1 over 2x plus 1 all squared minus 1 over 2x plus 1 all cubed. And remember, I said in the beginning, you can do this by partial fractions. If you did partial fractions, you would have found that I think I called a over 2x plus 1, that would have turned out to be 0, and the other two would have been 1 and minus 1. You would have got that. And of course, these are linear adjustments. You can write to the minus 2 to the minus 3, and you can just integrate and get the answer we got a few seconds ago. Okay, so I'm not going to show that. It's enrichment material. Some of you might want to try it because it will improve your skill and your overall understanding. So it's all good. Okay, the next two, we can fit them in practically one line because they're very, very straightforward. The first one is integral of 4 minus 5x to the power of minus 1 dx. That's number 60. And this is written in a very stupid way, just purely trying to confuse us because they think, okay, we might increase the power by 1. This is not anything about increasing by 1. This is simply a log 1 over 4 minus 5x. That's the normal way the brain picks it up. And this, of course, is log mod 4 minus 5x. And we need to adjust the chain from there, minus a fifth at the front plus c. And that's all. Question for you, I'm not going to answer it. Is that the same? Minus a fifth log 5x minus 4. Okay, so question mark. I've just flipped it the other way around. Is that okay? I'm not going to answer it. Number 61, integral of 1 over 4x dx. Very, very simple. I see this, by the way, as a quarter times 1 over x. So that's simply 1/4 log mod x plus c, and that's it. Okay. I know from experience, loads of students when they do this particular one, this arises, they won't give you something like that on the exam, but this forms exist after you do a substitution, you'll have it in U, possibly. So you might be having something like that, and then I see, of course, a quarter log mod 4u. So is that okay? That is the question now. Will you get marks, or is that wrong? The answer is most marking schemes that I've seen in recent years, they will accept it. Let me just show you what happens, just very, very quickly for your understanding. Let's look at this. Somebody didn't do log mod x, and they put a quarter log of mod 4x plus c. Technically it's correct, but it's not really, I don't like it personally, because you can actually write this as a quarter. I'm going to use a bracket and split this log using the rules of logs. So this is a multiplication, so that implies originally it was an addition. So we got log of x plus the log of 4, or you could have it the other way around, plus c. And when you multiply your bracket, you would have got a quarter log mod x plus a quarter log 4 plus your c. So you're wondering, okay, what about him? Okay, the answer is you can dump him. It's a constant. So you can shove him on the C, and if you want, you can relabel this C into a D or whatever. So the answer, the true answer in its simplest form, is this bit here. And personally, if I was writing a marking scheme, that's my I don't know, I have a dislike for this, personal dislike. I wouldn't accept this as an answer, because by the same argument, this will also be a correct answer. And I should give you, of course, if you were just totally perverse or mad and you wrote me a quarter log, I don't know, 37/13 of x plus c. Is that correct? Of course correct. It's just a constant again. You're going to have a quarter log of 37/13, which you can dump in your c. But why? I mean, the correct answer in the simplest form is that. But putting everything aside, as I said in the beginning of this integral, this form, usually it will be accepted for most boards at the moment in the UK. So do not panic if you're just thinking, oh, I might miss that, or I was thinking that was a log of 4x. It's okay. Next question is also straightforward, number 62. But it does involve a little bit of working. So, board is getting worse and worse. Very, very smudgy. I can see my writing from the previous question. Okay, it's 62. Integral of 1 over x plus 1 x plus 2 dx. I don't want to say a lot about that. If you should really recognize this as partial fractions. So we're going to do our partial fractions. Shall I do workings for this one? I'm going to write the answer for this particular one, but I'm sure you can do your workings. 1 over x plus 1 plus, times x plus 2 on the bottom is something over x plus 1 and something over x plus 2. I'm going to do it in my head sort of thing, but cover up. So forgive me, as I said, please do full workings for this yourself if you're not sure what I'm doing. This is -1, so that's going to be a 1 over this, and it's got to be a -1 on this, so I'm going to put a minus here. Okay, and just double checking it before I move on. I've got an x, minus x cancels, and I've got the 2 minus 1. It's all correct. So when you do your partial fraction, you'll get this particular answer, and the standard logs, no change, nothing. So this will be, of course, log of mod of x plus 1 minus log mod of x plus 2 plus c, which of course you can have it as a single log, because subtraction means you can divide inside the single log x plus 1 over x plus 2. So that's all good. Oop, drop my pen. Okay, number 63 and 64. These are very special. They're two sisters, if you want, symmetrical. And just to illustrate something very, very important, we have the x plus 1 over x, and we have the x over x plus 1, dx and dx. Okay, one is immediately doable, the other one requires a little bit of work. Okay, this one is the nice one because we can split it. Okay, x divided by x is 1 plus 1 divided by x, just 1 over x, which suits me because of course it integrates to a log. So the answer is of course x plus the log of mod of x plus c. Question done, nothing else to say. This one, there are several ways you can do this one. Most teachers will say for something like this, please do a little algebraic division, long division, whatever you call it, and because this is improper, blah, 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 and eventually you will get something that you can actually integrate. Some people say use the substitution, u is equal to x plus 1. Okay, that will also work. It's fairly decent as well. Okay, it's not too bad. This particular one is probably better to manipulate it, however, and split it. So I'm going to show the workings here. So you can do it by substitution. Please take your time. I'm going to create an x plus 1 on the top. This will allow me to split the fraction. And of course, looking at the top now, I need to make it worth x. So I need to take away 1. And now splitting. X plus 1 over x plus 1 is of course 1 minus 1 over x plus 1 dx, and of course this particular one will integrate to x minus the log of mod x plus 1 plus c. Okay, so this is this one, and the 64 is this one. Okay, number 65. Number 65 is one that I'm gonna do in a few ways because it's important to see a few ideas. Not a difficult one, not an involved one. It's a gift if you get that in your exam. It's actually very, very straightforward. So number 65 is the integral of, we got the square root of the denominator, which is 1 minus 2x squared. And on the top we have a 4x, just double checking everything is as I thought it was. Okay, bottom differentiates to the top. It almost looks that way because of course if you just look at the argument of the square root, you might be fooled to actually say it's 4 minus 4x. Oh brilliant, no it's not, because we got a square root around it, so that's not it. So it's not a lot of things we can do for something as ugly as that. Probably a substitution. The first substitution I'm going to use is what most people like to use, which is u is the bit inside the square root. So 1 minus 2x squared is my substitution. Immediately you differentiate it. Du by dx is minus 4x, and then we make dx the subject. Dx is du over minus 4x, and we're putting things in. I leave the 4x on the numerator. I called just this bit u, so, and at the same time when I write it u to the half, so that's for the square root. Okay, and my dx is du over negative 4x. This is brilliant, and it's brilliant because the 4x is cancelled, so I don't need to go and replace x's. So I'm going to rewrite this as, I got a negative there, so let's not forget, minus, and this u I'm going to write to the top, u to the minus a half, du, and now it's just increasing the power by 1, so u to the half, and 1 divided by half is 2, but let's not forget there was a minus there, plus c. And another thing to remember, we need to go back and put our substitution back in. So we're going to have a minus 2 there, and our u is 1 minus 2x squared to the power of a half plus c. So it's not bad at all. I didn't say that was as I said, it wasn't a bad substitution or something that should be causing you problems. But I'm going to do it a second way. And the second way is I haven't actually done in this revision session anything that has square root substitutions. In other words, u is the entire square root. So let's do this one. So this time I'm going to say u is the whole of the square root. So u is the square root of 1 minus 2x squared. You're advised to square your u before you do anything in this type of scenario. After that, you will differentiate, looking for the red pen here. Okay, after that you will differentiate implicitly this equation. So you're going to get 2u du by dx. If that doesn't make sense because you haven't done implicit differentiation, please ignore this particular approach, okay? It will make sense once you've done implicit differentiation. And now differentiate that to a 0 minus 4x. I'm going to tidy. 2u du is equal to minus 4x dx. Make dx the subject, so we got dx is equal to 2u du over minus 4x, and I have a factor of 2 that cancels there. So what I'm going to do, first of all, write the minus at the front, so don't forget. 2 over 4 is a half, so I'm going to write this at the bottom as a 2, and I'm going to have a u, an x, and let's put the du on the side there. It doesn't really matter. Okay, so that's my dx if I use a different approach, and I'm going to do the workings for that here. So that's an alternative. Let's see what happens when I do this. 4x, leave him as he is, he's happy. And I call this whole thing, the whole square root is my u now. So that's a u. And my dx there, my dx now is at the bottom there, minus u over, what the hell is that? Oh, so 2x. Can't even read my own handwriting, great. I hope you can read mine. Okay, so what happens there? Well, it's going to be a minus, first of all, I'm just taking care of that. And then the u's cancel, and then the x's cancel, so that's even better. So what I've got is 4 over 2, or just simply minus 2 to be integrated with respect to u. And of course, this will give you minus 2u plus a constant. And if you put, of course, your substitution, which is substitution is, of course, the square root, it will give you exactly the same answer. Okay, me personally, I prefer square root substitutions. It's a matter of taste, really. In an exam, usually, even if they give you the substitution and say, okay, use this particular substitution, it often says by using this substitution or otherwise. So if you don't fancy one particular one, you can actually try the other one. So if you don't like a square root, you can try the non-square root one. Although me, again, I will advise you in an exam to please stick to the advice that they're giving you. In general, they try to make life easier for you rather than harder, okay? So we're going to the next one, which is number 66. Number 66 is not a mess. Okay, 66, x plus 1. It's not not a mess, it's just I'm very tired, and I just looked at it and I said, oh no, not this. 66. Okay, what's going on in there? Is it some kind of substitution? Can we call u the denominator to break it? It looks like it, but it isn't. We got to be spotting something else on this denominator, which is very important. First of all, just check bottom differentiate to the top. Of course, that's the first thing we should have checked. That differentiates to 18x. We got the x on the top, but we got this plus 1, this annoying plus 1. It doesn't work. So if you look at this denominator closely, you should be able to see that this is in fact a difference of squares. So that's 3x minus 1, 3x plus 1, and on the top we have an x plus 1 dx. So these are partial fractions. Do I do this by cover up? In my state of mind at the moment, probably I shouldn't, because I have to substitute there a third and minus a third, and it's just a mess. For this one, because I'm tired, I'm going to show a full method, okay? I'm actually scared of them at the moment. If you want to know the answer, they're laughing at me, they're intimidating me, so I'm going to just take care of them in a safer way. So 3x plus 1, this is identical to something over 3x minus 1 plus something over 3x plus 1. Okay, what happens there? Equate tops. X plus 1 is identical to A 3x plus 1 plus B 3x minus 1. All right, I'm looking at this line. It's an identity. We can substitute in there anything we want. I'm going to put x is equal to positive third. So I'm eliminating this item by putting a third in there. So if I do that, so I go a third plus 1, which is 4 thirds, is equal to, I'm putting a third in there. A third of 3 is, a third of 3 is 1 plus 1 is 2, 2a. So a, I don't like the look of that at all, is 2 thirds. I have the answer up there, so I'll check it afterwards anyway. So let me just write up here. And so we got the 3x minus 1 and something over 3x plus 1. And the a is the bit which is above the 3x minus 1, and it came out to be 2 thirds. Okay, and I'm going to put now if x is equal to negative a third. So this time I'm eliminating this bracket. So I have negative a third plus 1 is negative 2 thirds here. Sorry, I beg your pardon. Wait a second, I'm putting minus a third in here. So positive a third. Negative a third, positive 2 thirds, minus a third plus 1 is equal to, putting x is equal to negative a third will kill this bit, but I will have in there 3 times negative a third, which is minus 1 is minus 2, so it's equal to minus 2b. And therefore my b will turn out to be minus 1/3. I want to put the minus there and write the third like this. And before I go any further, because these are looking not nice at all, I'm going to just check by adding the fractions in my head. It's worth doing this sometimes just to check if that works. 2 thirds of 3x is 2x minus a third is minus x, which is x. And then we're having 2 thirds from this bit here minus a third, which is plus a third, which is plus 1. So it looks like we've done it correctly. This is very ugly. I didn't expect that. Okay, do we write this 3 at the bottom? Many teachers say please do. I personally prefer to have it like this, because not about looks for this. This is about being able to see your integration. So this is a log on when it's integrated, 3x minus 1 modded. This is the coefficient, and we need another divide by 3 from this 3x. So it's going to be a 2/9. 2 thirds divided by 3 is 2/9. And then we got the log of 3x plus 1. And we got a negative a third. So negative a third divided by another 3 should give us 1/9 plus c. I was going to check this answer for this particular one because it was not something I was expecting. 2/9 log 3x minus 1 minus a 9th log 3x plus 1. Yes, we've done it correctly. Okay. Normally there'll be nicer numbers than what we just faced. Okay, number 67. We're going to go up to 69. I don't know how long this lecture will go, but I really want to finish that page. 67 is not bad. It's the integral of x sine 4x. X sine 4x, product of 2 different mathematical families, algebraic versus trigonometric. We've done a very similar one. Was it sine as well, the previous one? Yes, it was x sine 3x. That was number 58. This is x sine 4x. So it's practically the same, but for the difference for the argument of the sine. So I'm going to put the x on the top left, and I'm going to put the sine of 4x on the bottom right. Differentiate the x, 1. Integrate the sine of 4x. Cos 4x, cos differentiates to a minus, adjust it, and then it needs a quarter in front of it. And now, with integration by parts, the way I do it, this is equal to product of this. So that's minus a quarter x cos 4x, x cos of 4x, minus the integral of the product of this diagonal, and that's going to be minus a quarter cos 4x, minus a quarter cos of 4x. Switch that into a pluses so we don't waste the line, and then we can just finish it off. We just got one more integration to take care of. I hope this board makes it to the end of this lecture. Look at the state of it. This is I'm fed up with this. I have to show you. This is a Stadler, German overpriced piece of crap. Okay, I should know for next time. I don't care if they sue me. The pens are absolutely rubbish. Very expensive stationery, and I was expecting quality. Okay. This is now the cos of 4x, needs to differentiate the sine of 4x to give me that. Sine differentiates to a plus, so that's all good there. He also needs to take care of this 4, so I need to divide by another 4, 1/16 sine x plus c. And this is now done. That's number 67. Number 68 is one that often we forget how to do, and we need to remind ourselves of the technique. The log of x. Okay, how does that integrate? Is that 1 over x? The answer is no. Log x differentiates to 1 over x, but it doesn't integrate to that. A lot of people, after a little bit of practice, they memorize this result. I certainly know the answer to that is x log x minus x, but in an exam, you cannot just quote it unless you're using for something else. If it says to you, integrate that, you must show workings and where is it coming from, okay? So this is done by parts, by writing usually 1 times the log of x dx. And then you do another little grid. I'm gonna do it here. When you're having a log in your parts, the log goes on the top left, is to be differentiated. And the 1 that's just produced in there is to be integrated. Log of x does indeed differentiate to 1 over x, and the 1 will integrate back into an x. So the answer now will be product of this, which of course is x log of x, and you should put really mods there, okay, minus the integral of this diagonal. And x times 1 over x is just simply 1 dx, and of course on the next line, I'm just going to write it here. I can't be bothered to, because this is going to be a mess even worse by the time we finish this. And 1 will produce, of course, a minus x plus c, and that's the answer. It's as simple as it gets. And we reached our very last integral, number 69, and I'm pleased to say this is a one-liner. We're going to do it here. So number 69 is 4 over 2x minus 7 to the power of 2. Okay, how do we integrate that? Sometimes you can freeze an exam and you might just be saying, okay, what do I do with this? And you might be doing silly things such as substitutions or anything like that. By the way, substitution will work if you use u is equal to that. Totally unnecessary, of course. This is just a linear adjustment. You need to write it on the top as 4 bracket 2x minus 7 to the power of minus 2. Now this is a linear expression, ax plus b, and therefore it will integrate by increasing the power by 1. Okay, so this starts from the bracket 2x minus 7 to the power of minus 1, added 1, don't forget. And then if we differentiate, we're going to get a negative 1 from the power coming to the front, a times 2 from the 2x. So we're going to get a negative 2 that will come to the front. And of course, this will go to the correct power there. So the 4 that I'm seeing there, it needs to be divided by negative 2, and 4 divided by negative 2 will give me that. And if you want, you can write it. This particular one is probably neater if you write a minus at the front, a fraction, not 1, sorry, because we've got a 2 at the front, that's that 2 there, a 2 over 2x minus 7 plus c. And this is in fact now number 69. I'm so pleased we finished with this one because the board was having enough. And on that note, who's laughing now? I'm certainly knackered tonight, and I'm glad I finished this one. This was lecture number 6. I will add another lecture, guys, very, very soon, maybe in 2 or 3 days' time. So I hope you join me again, and I hope you find this useful. Okay, bye for now.